Okay, welcome to video 2.4. Okay, now I'll talk a little bit more. I want to discuss something about how in practice, okay, we just get an example, a very easy example, how we got calculated an estimate of theta hat. Okay, now in that case, what we had was L of theta just equaled theta squared times 1 minus theta. And this is a pretty simple function, okay? Now, often when you do this in practice, the function is going to be so complicated that you can't even write it down. You're going to need to program it in a computer. We're going to do somewhere it's in a spreadsheet where it's still very complicated. So even the likelihood function is too complicated to write down by hand, okay? So much less are we going to be able to calculate the derivative by hand, okay? So before, before we had a closed form solution of the derivative of our log likelihood. It was just this. We can write it down, okay? Very often, I'd say, maybe usually in practice, you can't do that. Okay, so what do? Okay, the answer is you use a numerical derivative. Let me show you what that means. Okay, so first, let's define little l of theta. That just, I'll use the three marks like this to say is defined to be log of L of theta. Okay, now what we're going to do, I suppose we have this little L of theta. It's too complicated to write down, but we can write it in a computer or an Excel spreadsheet. Okay, and we can feed it different values of theta, and it will spit out what L is. Okay, so suppose we've done this, and suppose we can graph out or get a very good approximation. We feed it a few values of theta and tell the computer spit back out what L of theta is. Suppose we get kind of a graph of a line. Okay. If we've done that, we can do what's called, we can calculate a numerical derivative. And the way we will do that is, you have to remember, okay, from freshman calculus, the definition of a derivative. So I'm going to call it L prime of theta, and that is just defined to be L of theta plus d minus L of theta divided by d, and here what we want is limit as d approaches 0. Okay, so that's the definition of a derivative. Now, when I say a numerical derivative, what we're going to do is, rather than literally take the limit as it equals 0, we're just going to pick a d that's very, very close to 0. So what we're going to do is we're going to feed the computer. We're going to say, let's pick a theta. Let's pick a theta plus d, and then feed it into the computer or the Excel spreadsheet. We can get L of theta. If you like, call that L theta sub 0. It's some value of theta that we've picked. So that's L of theta sub 0. Then that would be L of theta sub 0 plus d. Okay. And then what this value is, it's the slope from that point to that point. Okay, now, and as you should remember from calculus, so that slope might not perfectly equal the derivative of that point, but the slope is going to be very close to the slope of that tangent line that I've drawn. So if we make that d very small, this numerical derivative is going to be a very, very close approximation of the true derivative of at L L of theta sub 0. Okay, so once we're able to do that, then we can have a computer. We can calculate the numerical derivative. Then we can try different values of theta zeros or different values of theta to find a numerical derivative that is very, very close to 0. Once we've done that, that will give our estimate of theta hat. Okay. And, okay. Let's see how much I've done. 5 minutes. You know what? Let me give. Let me just talk. I'm going to give maybe 2 more minutes of describing what I'm going to do. Okay. Now, let's see. When we compute, you say, well, you know, we're gonna use a d, and what we're gonna do is when we calculate a numerical derivative, we're gonna pick a d that's very, very small. So you program into the computer d equals 0.0001. Okay, you know, d equals 0.00001. Okay. Now, you think, well, the best way to approximate the true derivative would just be to set that d as small as you can. You know, put d equals 0.30 zeros and then a 1. Okay, why not make it as small as you want? Well, here's why there's an art to it, and you can't do that. Why what I described does not quite work. And you got to remember back to 5th grade math. Okay, so we use a 10-digit decimal system. Okay, so we have 10 digits, and as a consequence, 3 does not divide into 10 perfectly. So if we want to describe 1/3, we can't use a decimal. We have to have 0.33333, and it goes all the way out to infinity. Okay, the same thing happens in a computer. Now, a computer uses a binary decimal system. It's just zeros and ones. But for the same reason, some numbers cannot be represented perfectly with a finite number of digits. So, for instance, if we put in, you know, 0.001, 1/10,000th, okay, that might not be able to be represented perfectly in the binary system. So you might need an infinite number of zeros and ones in the computer to represent that 1/10,000th. Now, the computer doesn't have an infinite number of digits, but it might have 1,000 or 10,000 in it. So you can get very, 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 very close. Okay, but the problem is if you give it a d equal to, you know, 1/1,000,000th or 1/quadrillionth or, you know, 10 to the negative 100, then the computer, which only has 1,000 digits or 10,000 or a million digits, cannot represent that number you've just given it. That decimal number, the computer cannot represent it perfectly in a binary system. And the ratio of how it will represent it versus what the true value is will actually be worse. It'll be farther away from 1 the smaller you pick that d to be. Okay, so there's an art. So what happens is you want that d to be very, very small to be a very good approximation for the derivative of the true derivative. But when you make that d very small, the computer is not, when it uses its binary representation, is not representing that d very well. Okay, so I want you to skim over that reading by Gould and Scribney, and it talks about this problem. And basically, the rule of thumb, you know, for doing this, it's an art. So you make d too large, you're not representing that function very well, the derivative. But if you make d too small, then the computer can't represent the d very well. So you need to pick kind of an intermediate value of d. And what Gould and Scribney talk about, usually with the best system to do, is to pick the smallest number that the computer can represent perfectly. Okay, so if the computer goes out to 10,000 binary digits. So you put 1 to the 10,000th, whatever that number is. So, and then you take the square root of that, and it turns out that's your optimal D. Okay, so let me give you a hint. When you do your homework problem, you'll probably want to pick D equal to something like 1 over 1,000 or 1 over 10,000. If you start getting out to 1 over a trillion, you're going to run into problems. Okay, so keep that in mind. Okay, so that is video 2.4. So see you in 2.5.